hello. Awesome. Great. So, hi again, everyone. I'm here for talk 2 of 2 today. It's a different talk. But actually experiences going back more than 20 years. And I realized that there's some experience to share here and things that I've done in and that can be helpful to the TE community. That's what this is about. The title is Token Engineering Verification. Verification is a very particular word. So token engineering verification from TokenSPICE EVM simulation to AI-powered CAD. Let's get started. Okay, so as an outline, I'm going to motivate the problem by just talking a bit about dollars and DeFi hacks. Then I'm going to give some history about circuit verification. Then I'm going to bridge from circuits to tokens for verification, and I'm going to discuss what this looks like in token land, where we're at today, but where I dream of us being in 2 years, 5 years, and so on, and then wrap up. So let's get started. So there's always stats on crypto because everything's open and stuff, and here's some stats from last year. There was $3.8 billion in hacks. Of that, 82%, $3.1 billion, was in DeFi. Of that, 64% was in bridges, and 10% was in flash loans. So 75% of the DeFi hacks last year, of the 3 billion hacked, was in 2 things, bridges and flash loans, which is kind of a problem, right? Overall, I mean, the hacks is a huge problem, but it comes down to even just 2 things to the biggest. And the hacks keep growing, right? Crypto keeps growing, so the hacks keep growing. And it's also a sign, though, that we haven't, we're not there yet in the tooling to stop the hacks in their purchase. We're getting better. But I'm going to describe here. I think, is there some mic going on back there? Because it sounds like someone's, I don't know, opening a candy bar. Okay. I'll take the candy bar, though. Thank you. Awesome. Okay. All right, so basically, we can do better, is the point. So let's just talk a bit about the status quo when it comes time to verify your design. Let's say you're a protocol organization, maybe a startup, maybe older, and you write your Solidity smart contracts, and then maybe you write some unit tests, do some system tests. You hire an auditor. If you don't want a good one, you wait a month. If you want a good one, you wait 6 months or 9 months. And then maybe you're going to do formal verification with Slither and these sorts of tools. And people are starting to play around with LLMs as well, right? So that's kind of the status quo, right? And working with the auditor, you iterate back and forth, and eventually you're good. Once you go live, or maybe before, you might engage things like Immunify for ongoing bounties, and that's also a best practice. So that's the status quo. Now, before I talk about the problem, I need to download to your brains something which is, what's the difference between analog signals or systems versus digital signals or systems? So the core is the following. The real world, in real world here, in real life, everything is analog. It's continuous value. Time flows, right? But along the way, inside computers, we discovered that it's much easier to do computing if you abstract it in 2 particular ways. You abstract by saying things are just true or false, on or off. And you abstract with chunk, chunk, chunk clocking, okay? But if you loosen from, and that's when we do programming and all that, it's all digital computers, right? So we talk about the world being digital, or going digital. But even in this very digital world with silicon and computing, analog is still there, everywhere, right? And a way you can think about it is, there's this balloon that keeps growing, growing, growing. And inside the balloon, that's all the digital stuff. But the edges of the balloon, the balloon shape itself, that's the analog. And then there's the rest of the world. So analog is always this interface to the world. So digital is easier to reason about, but you can't abstract it all away, right? You need to interface with the real world, et cetera. And that's where analog comes along. So this is just very good to understand. Okay, so going back to verifying tokenized ecosystems, our blind spot is analog, okay? So all these things I gave before, they are all verifying the logic of smart contracts. Logic is a digital thing. It's a Boolean thing, right? We have large gaping holes in our approaches. For example, analog side, gaping hole. Flash loans, it's an analog thing, right? It's someone basically, instead of just putting in a little bit of liquidity or something else, it's a huge amount, right? Or incentives that could kill sustainability. The last couple of talks talked a lot about that, right? Also, when you have analog interacting with digital, this is called mixed signal in circuit land. Because we're not modeling analog, we're also missing the mixed signal. In analog land, this is things like A to D converters, and so on. And then we're also missing typically beyond one virtual machine. This is bridges, right? So we might have chain 1 with one virtual machine 1 that we might have tested, but are we also doing chain 2 with virtual machine 2 and bridge, often with its own VM or otherwise, right? And the interactions among that. This is a blind spot as well. So it shouldn't be surprising that we have billions of dollars worth of hacks. We're not properly testing this stuff, folks. And it's not just testing, it's verifying, it's knowing that you've got it, right? So how do we fix this? And to me, it's actually, well, a bit of history. In fact, I think I'm going to get there next. Yes, so a bit of history. Before I came into blockchain land, I spent almost 20 years in the world of semiconductors, and specifically designing CAD tools for semiconductors, specifically designing analog CAD tools to verify analog chips. So this, to me, is near and dear to my heart. And as I've seen things grow, especially in DeFi, it's become really, really obvious to me what could be done. And this is the first time I've actually spoken about it publicly in a big way. And it's my pleasure to share with you where we are and what we can do. So first, though, I need to download to your brains about what circuit land looks like. What are these tools like, et cetera? And then I'm going to mirror that into token land. OK, so the semiconductor industry. First of all, this is a massive industry. It's one of the biggest industries on the planet. Annual sales every year is $550 billion. And the total market cap is about $3.2 trillion. So this is huge, right? And here are some of the biggest companies. You'll recognize the names, are most Samsung, NVIDIA, Intel. There's lesser known ones like Broadcom or TSMC. TSMC manufactures more than half the world's chips and more. And why is this so big? It's because chips are everywhere. There's a chip inside here, probably 5. There's probably 30 chips inside this computer. There's 20 chips or 30 chips inside your phone. The data centers, everything. There are chips all around us. This is silicon. It's the PCB and the chips on top. Okay, so this is a massive, massive industry, and it's changed everything. But if you think about it, right, if I'm a design team designing chips, there's maybe 10 people, 30 people, 50 people max. Maybe you've got 3 months, 6 months max to design and ship a chip that has 20 billion transistors, right? How the heck do you manage the complexity of that? You're not going to do it manually, right? You actually do it with software. And it's not just getting the thing out the door. You've got to minimize power. You've got to maximize performance. You've got to minimize area. You've got to maximize yield. And you've got to all do it within hitting the time to market. And that counts for a lot, right? So there's a huge dollar incentive to make those numbers great, right? People are willing to spend a lot of time and money to do this. And so, like hinted, software can help a lot. So there was actually an industry born dedicated for this. There was some tools beforehand, but in about 1980, there was actually a breakthrough textbook by Carver Mead and Lynn Conway, which laid out the different layers of semiconductor and pointed to the CAD tools. And that was really the true birth of the EDA industry, electronic design automation, or call it the CAD industry for circuits. And it's a $16 billion industry on its own. So maybe, yeah, sure, it's whatever, 5% of semi, whatever. But that's still a huge industry on its own. This is just for people making tools, making software to design the chips with, okay? So, and it's this industry that I interacted with. But of course, the customers are the Intels of the world. Okay, so if we look inside the tool types, remember, this industry is all about making tools for chip designers, And the chip designers, these people are trained as electrical engineers. Maybe they go on and do a PhD in analog circuit design or something else to specialize in. And so there's, the way the industry is shaped, there's 3 big players, Cadence, Synopsys, and Mentor Graphics, which is now part of Siemens, okay? This is just from the Synopsys site. If you look at its tools, it's got like a whole bunch of different categories, right? Because it's huge. But there's 2 main categories. There's a category for design, and there's things inside that, 3D IC design, test automation, and so on. And then there's verification. And verification includes simulation, but also a bunch of other stuff. So there's a bunch of different point tools for the different steps of the flow. And you might ask, okay, well, what about the steps of the flow? And actually, I'll get to that in a second. But I mentioned the difference between analog and digital before, but how does this manifest as a circuit? I'll just give you a list. So for digital, at the smallest level, you've got things like AND gates and OR gates, but then these get combined to larger and larger sizes, adders, multipliers, then muxes, then GPUs and CPUs. You've also got things like digital filters. You've got memories. Those are officially digital. When you try to design them, it's more analog-y, but they have a digital interface. And then so you saw this. And by the way, when you go to design digital circuits, you're generally writing code. In fact, one of the leaders of Intel, I think it was Andy Grove, had a quote something like, microprocessors are simply frozen code, right? So this is an example of people writing code. Sometimes they even write C-like code called System C, and it compiles to RTL, register transistor logic, register transfer logic, sorry, and then that compiles to physical, et cetera. But when people are designing digital chips, it's writing code, okay? And of course, it's always like easier to reason about when things are digital, writing code, all of that, right? So if you go to the analog side, the analog types of circuits are things like, you know, your cell phone. How does it talk to cell phone towers back and forth? That is RF receivers and transmitters or transceivers, right? You've got power management. You know, how does the battery feed the rest of your cell phone? You've got clock generators to power the digital stuff. You've got A to D converters, D to A converters. You've got amplifiers, like I'm using right now, to amplify how I'm speaking, and analog filters. So you've got, and this is, you know, a lot of the core building blocks. There's more, but it gives you a feel. And interestingly, notice how these are mostly about the interface between the real world and digital. So this is not going away. A lot of people have thought, you know, with the rise of digital, analog circuits go away. They're not, right? They are as important as ever. And quite often, it's, you know, maybe analog has maybe 10% of the mind share, but it's often 80% of the problems, right? Especially when it comes to verification. And that's why I spent a lot of time there, because I wanted to help. So overall, there's actually two types of EDA tools, and we've seen some of the previous talks talking about, you know, different steps, DDD, and so on. In circuit land and EDA land, it's really broken up in two places: design and verification. Verification includes simulation. In terms of market size, 2/3 of the market size is all about verification, simulation and verification. So if you think about the tools right now that we've been seeing discussed before here in Token Land, it's really been a focus on design. But the real challenges are in verification. And we see that we're not there yet because of all the hacks, okay? So then you need to say, okay, analog and digital. So you've got digital design, digital verification, analog and mixed signal design, analog and mixed signal verification. It's 4 different categories, and each of these have many subcategories. But this is how to think about it. I did 2 startups and a PhD in this world. So my first startup was about analog and mixed signal design, and my second startup was verification. So I got to straddle both. Okay. Let's talk about digital CAD, digital EDA. So this is, and design. I'll start with design, go to verification. This is an example using Siemens in this case, so Mentor Graphics tool. And notice how people are writing code up here. And in this particular case, it's writing code and using a compiler. You know, we're used to writing code using a compiler to go to assembly, then machine code. Here, the compiler goes to RTL, and then you can actually take the RTL and go to physical mask layouts, manufacturing instructions, okay? So this is an example of a digital design tool. But of course, once you've done the RTL and so on, then you want to go to layout. So this is still part of design. And remember, there are lots of different design tools. Usually for different niche problems, there's competition, all of this. And overall, there's a whole bunch of different flows too. So Synopsys has its recommended flow using the Synopsys tools. Up here, we've got the design, and then system design and digital design. And then the whole bottom 2/3 is all about verification. And there's a big also subset of verification called sign-off, but it's just part of verification. So it just helps to emphasize how important the verification side is and how that's such a blind spot here in Token Land. Okay, here's an example of digital design and verification. I just did a Google search for the top 3 firms, and then digital design flow. And you look at it, and like even just from this first page, right, there's 10 different flows. So here in Token Engineering Land, we talk about the token engineering flow. There's not going to be the token engineering flow. There's always going to be 10 or 20 or 30 different flows. And as we use tools more and more and more, it's going to be guided by the tools, and there's going to be an interaction back and forth. This is really important to understand. And I strongly believe this because this is exactly what happens in this industry, the $16 billion industry that absolutely powers this $600 billion industry. So this is how it is. Okay, so that's digital. Now I'm going to talk into my sweet spot, analog EDA. I'm really going to drill into this. Okay, so first of all, when you want to enter a design, you don't have the luxury of typing in code, right? So analog designers, they think in terms of dynamical systems, very much like control systems. And they actually draw, this is a transistor, and then they draw the wires between them. And this is an example of an op-amp, it looks like, an amplifier, basically. And this is using one of the leading, in fact, the leading tool for schematic entry called Cadence Virtuoso. And we've seen some emergence of this in Token Land, right? Machinations has a pretty cool schematic editor, and there's more. Great. And this is, a starting point for entering the designs. And there's, off-the-shelf free schematic editors too. There's probably 30 schematic editors out there in the world. But then you can also get to fancier design. So here's a tool that my previous startup developed called Fast Design Sweep. And in this case, it's doing sweeps, but instead of across 3 or 4 variables, it can go across 100 variables, yet still not break the bank computationally because of some fancy AI under the hood. I'll get to that later. So this is an example tool to help explore the design space. But then also you can have tools for verification. And it turned out that this only got really good once we could have, once compute power was fast enough for SPICE in the loop. And I'll get to that too. So this is an example of a verification tool to find worst case corner conditions. So in this case, in circuit land, the main 3 are process variation, voltage, basically is the voltage supply 1.2 volts or 1.4 volts? And then temperature, is it minus 20 degrees, is it plus 50? And you basically have to run through the whole space and find the thing that really breaks the design the worst, okay? And to give you a feel, this was a highly successful tool. Basically 19 of the top 20 semis adopted this, everyone except for Intel, because they build their own stuff. Every single chip that NVIDIA has shipped since about 2010 runs through this tool. So it's become standard practice, and they do this because they don't want their stuff to break, right? They've got GPUs to ship to the crazy AI people, et cetera. So this is what they do. So that's to give you a feel about the higher level of the tools. I'm going to drill even deeper now into some of the pieces below. So the beginning of this all is SPICE simulation. And so to give you, to help motivate that, here's another analog circuit. It's another amplifier, basically. And the question is, how do you maximize its gain time bandwidth? And if you really want to be like a pro analog designer, to really know what you're doing, you're going to go get a PhD. And there's, say, 5 or 10 really top schools in the world for this. There's probably 100 great schools for digital. Analog is much more rare. I had done my first company, realized I really didn't know analog design that well. So I went to one of the top. It was the only school in the world, KU Leuven in Belgium, that had great analog designers and great CAD. So I went in there and I subjected myself to the pain from these world-class designers and got them to teach me analog design. One of them is Willie Sanson. So he wrote a couple textbooks on analog design about systematic analog design. So instead of just flailing around, how can you design analog circuits in this very systematic way? And one of his big tricks was you write down the performance equations for this, and then you add one constraint at a time until you've removed all the degrees of freedom, right? And this is a very good design. And notice there's no simulation yet. This is all in your head. So you basically make sure you're good conceptually. And it's not easy to do. You really have to think in a very particular mode. But it's actually super fun too. When you get into it, it's like, wow. And I'm still not a great analog designer. I'm really like bottom 1%. But I had the great fortune to work with some really great designers. So how do you verify this, right? So you've done this all on paper. How do you verify it? And so along came this idea of SPICE. So as microprocessors were coming along in the 60s, right on the heels of that, because it was so close, so similar, people immediately realized they wanted to simulate circuits, analog and digital. So people started building these simulators in the late 60s and early 70s. And this guy, Ron Rohr, he started a class project. He got each of his students to build a piece of this simulator called SPICE, the world's first great circuit simulator. And one of the students just took it and ran with it. His name is Larry Nagel. This was out of UC Berkeley, right next to Steve Joy. So they actually licensed it, BSD, running on the BSD, the Unix as well. So basically, you take a netlist. It runs through the SPICE tool, and it spits out waveforms, basically. All text-based, and you can build the tools on top. So this came out in 1972, and this is an open source code. There's lots of open source SPICE now, but this is the roots of it all, SPICE. And so to elaborate on this, basically you do your manual design, the Willie Sansons of the world, drawing your equations out, et cetera. And then you enter the netlist. It's basically text like that. And then you run SPICE and you get your results. And that's your way of basically very simple verification after you're happy. So that's AVFlow, and that's been a standard flow for analog circuits for many years. Here's an example of the netlist. There's basically a bunch of lines to declare, for example, this resistor goes from node 2 to node 0 with a resistance of 10 kilo ohms. And it lays out all the different parts, and on the bottom it specifies the different analyses. Do a transient analysis, do an AC, whatever, okay? And by the way, SPICE has, since 1972, for 10 years, 20 years, it grew, but it's still around in a big way. So I did a Google search for SPICE simulation, and there's just a gazillion results, right? All these different variants of that. So there's an industry, given that analog, it's about $1 billion market just for SPICE simulation, maybe 1.5 billion, to give you a feel, right? So there's PSPICE and TSPICE and all of these different simulators, plus the big guys like Cadence have their own versions. Cadence's SPICE-like simulator, for example, is called Spectre. So this is a thing. But then, in the mid-90s, something happened. Computers got fast enough that you could start to realistically consider having SPICE in the loop. And SPICE is really nice because it's actually silicon accurate. These models of transistors have been calibrated against the process itself. Whereas everything before, they would try behavioral models and stuff, but it was off. So SPICE was really trusted, but until the mid-90s, you could only afford enough compute to run it once or maybe 5 or 10 times. But by the mid-90s, late 90s, you could afford to run it 100, 1,000, even 10,000 times, and clusters started to emerge too. So that's what happened, SPICE in the loop, and that's actually where I did my first company too. So you can basically have this emergence of SPICE in the loop tools, where basically you have maybe a manual initial design. You could also synthesize that, but that's a whole other story. But what the tool does, maybe for design, it might wiggle some widths and lengths and resistances, whatever. Run SPICE, see how it does, what's the power consumption, et cetera, and then loop back, iterate, iterate. You can have a global optimizer, local optimizer to minimize power, whatever, or you can run verification here too. So this emerged in the 90s, and several startups around this, et cetera. Okay, and so my first company was doing this for analog design to optimize designs. The second startup was for analog verification. And here's an example. Here's one for design using model building optimization, some AI. And here's one for analog verification. In this case, this is for a memory, a bit cell. So let's say you have a 1 gigabit memory. Each bit cell, assuming no error correction, needs to have much lower than a 1 in a billion chance of failure, say maybe 1 in 10 billion. So, for such that the overall 1 gigabit memory has decent yield, right? Because a 1 gigabit is 1 billion bits. So if you need 1 in a billion, 1 in 10 billion chance of failure, if you want to run Monte Carlo on that, then maybe you have to do 1 trillion simulations, right? You know how long 1 trillion simulations take? Even if one simulation takes 1 second, it's a long time. But companies were doing this. Qualcomm was actually running this stuff on clusters of 1,000 machines for a month just to verify their bit cell. But if you're smart about it, if you're sneaky about it, and that'll still only give you this, but imagine you can get up here with just 5,000 simulations, 10 minutes on a laptop. So there was a lot of value to get there, and this is actually what my previous startup did. And it made the Qualcomms and NVIDIAs of the world very happy. And you can do this for statistical, like tail simulation especially, but also for the worst case, right? In that case, it's finding these corner points like before. And in fact, to break down the SPICE in the loop tools from an analog side, so we can break it down for verification and for design. For verification, oh, excuse me. So you can start with nominal, no verification, that's just SPICE. But then layer in more and more and more stuff. You can layer in worst case analysis, Monte Carlo simulation. That's not too bad. To get to 3 sigma, you need 1,500 samples. High sigma Monte Carlo, though, you need, well, sorry. I've been talking too much, so thanks for your patience. So you need, 1 million to 1 billion samples there, right, to hit that. And so somehow you need to chop that down for sim time. And then for design, there's simple things like sweeps, but then you can do optimization locally, globally. You can do synthesis where it's actually wiggling the shape, like the components themselves, popping in a resistor, et cetera. And then if you want to be extra crazy, you can do it all at once. You can do synthesis, wiggling the variables, having worst case design, having statistical all at once. And that's for the really crazies out there, right? But it's actually possible. Okay, so, and then, I've already talked about some of these SPICE in the loop stuff, but to give you a feel, this stuff is all AI powered since the mid-2000s. How do I know that? Because I was helping to build it. And so this stuff that I showed you before, how did we get this tail here, which normally would take you, 1 billion simulations or 10 billion simulations, how did we get in 5,000? And there's, people might say, hey, importance sampling. But that only works if you've got 6 or 10 variables. But in importance sampling, the variance grows exponentially in the dimensionality. We would have, even for a bit cell, 30 variables. But then if you have a sense amp, you're talking about 10,000 variables and other things. So it just, the basic stuff didn't work. We needed new tricks. And we found in this case, one example, what you could do is you say, okay, I know the design is around 4.5 sigma, so I only need 1 million simulations. So I just need to figure out which simulations do I really, really need to simulate to verify. And so we would simulate ones, and also the things that have the designs. So you take a million Monte Carlo samples here, you don't simulate them, and then you take the ones farthest from nominal, because those have the highest chance, roughly, of failing. You build a response service model from that, an AI model, and then you use that to very quickly filter the simulations. So we were able to filter 1 million samples on 1 second on a CPU, because we had, just optimized the heck out of that. And that's what allowed us to, so you would filter, simulate the ones that were the most likely to fail, and then update your model and loop, 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 right? And so that's some, it sounds straightforward, but the devil's in the details. And then you could actually track convergence. And this is super useful, because then you can see if it's converging nicely here, it is, you can start to answer the question, can I trust it? And that was always the question. We didn't have these plots at first, but putting in there, it answers how can I trust it? Okay. And we did the same thing for past PVT. In this case, it could be cast as a global optimization problem. We used model building optimization. So imagine this is the true response surface, and we're trying to maximize the power. Then what you do is you take some initial random points, like here, random training points. You build your model, that's the red. You build your model, that's the red. And then you simulate there, and you build a new model, and you iterate, until you have until you've converged. And as an example here, this was the initial samples to build the model. And then it optimized, it's trying to maximize. This is when it found the maximal point. And everything after this, it couldn't find anything else. But by seeing this convergence curve, now you know you can trust it, because it hasn't found anything else. So that turned out to be really critical to adopting this thing. Remember, you can't get a formal proof on this. There have been formal approaches to this where you slice and dice things. But the state space gets so big so quickly that you can't actually truly approach it in a practical way. So you need to do things like this that are slightly heuristic, but in practice they work really well. Okay, so to give you a feel, this is the suite that my previous startup had done. And by the time we got acquired by Siemens, we had 1, 2, 3, 4, 5, 6 different key tools. Each tool had about 3 or 4 pieces of AI in it. So there's about 25 different pieces of AI in this. So this whole thing was AI powered. And it wasn't just us, there was others too. I just know this one well because I helped to build it. And so I knew it was under the hood. So this was already circa 2012 or so. So AI powered CAD in 2012 to drive analog circuits, right? And that was the state of the art. Now, it's gone that much further. They went full cloud, and Synopsys and the big guys are all advertising AI and stuff, but this stuff was there 10 years ago, 15 years ago. Okay, so I've talked about circuits. Hopefully you found that as a very useful download of how this industry was, right? And I hope you're feeling FOMO, right? I hope you're like, wow, I really got to get that into token land. And that's when I'm going to show you where we're at. Okay, so token engineering verification is a lot like circuit verification. There's digital, there's analog, there's a mixed signal, right? So in digital, you've got circuits, the discrete time clock stuff, et cetera. And analog, I've talked about all that. But overall, you've got a smart contract, and when it gets verified, I talked about it being very mostly digital, right? The auditing, et cetera. And the analog, though, this is where you have incentives. You have flash loans, you have bridges, latency and networks, all of this, right? The stuff that we haven't traditionally been modeling. And then the mixed signal is the combinations. So these things are very, very similar. Okay, so now what I'm going to do in the tail end of my talk is talk about token verification. I'm going to drill into the analog, which we're kind of missing. Some of the digital, and I actually helped friends from the digital verification world of circuits who did formal verification, et cetera. I pulled them into this world to help a few years ago, and I hope it made a difference. I don't know. And now, though, I see that we have work to do on the analog side. Okay. So first of all, as a baseline for analog, if you want to do this pro, you need a simulator that gets to the metal. The whole thing about SPICE is that it's not behavioral, it's not a higher level thing, it's getting as close to the silicon as you can. So we need a similar thing for token land. So when I say getting to the metal, I mean getting to the level of the Solidity implementation, which goes straight to the EVM, et cetera, right? Or other VMs, et cetera, too. So, no approximations, go as close to the metal as you can. So, so that's what TokenSPICE is. And now there's actually, I think, a few others. TokenSPICE, I first released it, I think, 2.5 years ago or so. And the whole idea is it's agent-based, and an agent could be pure Python, or it could be Python that's wrapping a Solidity smart contract, or an API or whatever you want, right? And the key thing is an agent has its own wallet, holding tokens, and you loop. Every block, it's another step, and each agent has an action, take step. And you can code out what that does for the Python agents. And for the smart contract agents, you don't code anything. It's just a thin wrapper of Python such that it all plays well together. So that's the heart of it. But then you can also track the metrics, the KPIs, et cetera, from this. OK, so here's an example of an agent wallet. It's just part of the agent. You know, they have their wallets. They hold different things. And critically, to make this not custom, you have the idea of a netlist. This is a specification of how the different agents talk to each other, right? So on the left, I'm creating a netlist where I'm adding a marketplaces agent, a router agent to send tokens from one thing to another, an ocean burner agent in this case, a minter agent doing ramped exponentials, and yeah, that one basically. So 4 agents. This is one particular netlist. But this is all open source in GitHub, TokenSPICE organization, TokenSPICE repo, and it's got lots of examples of netlists of different things. So there's the Python, but there's also the Solidity side, right? So any of these agents that are just simply the Python wrapping the Solidity, then it's straight up Solidity. So you can take any Solidity code you want, or any new code, and use that. Okay. So then the flow is very, very similar to what we had in analog circuit land. You do your manual design, where you draw out your pictures, you draw your schematics, whatever, manually on your own or with a schematic editor once it's come along. And then you enter the netlist, you type it in Python and Solidity, and then you run. You run Spice, TokenSPICE, et cetera, and you get your plots, right? So this is the basic idea, a basic flow. And critically, you can have EVM here, right? So now you no longer have to write a digital version of, say, a balancer AMM. You're just using the balancer AMM Solidity code directly, right? So it's obviously 100% accurate because it's there. So that's the flow. And then you can get fancier. Rather than just a pure manual flow, you can have TokenSPICE in the loop. So just like in the analog version, analog circuits, you have an automated tool here that chooses the next thing to simulate, right? Chooses a different amount for an LP to LP into, or whatever you want, runs TokenSPICE, iterates. And if you're trying to, say, do worst case verification, or then it tries to find, how will LPs lose the most money, right? And quite often it would just emerge as finding flash loans on its own, things like that, right? So this is an example for verification. And I really want to keep emphasizing the parallel to circuit land. It's so similar, right? It's uncanny. But that's great news because we've worked out how to do this in circuit land. Okay. So I'm going to show you some simulation results. So work that I did a couple years ago already. Without the EVM stuff is this Web3 sustainability loop, right? That is taught here with the token engineering community. And lots of people talk about flywheels, the previous talks, et cetera. So here's a very simple conceptual version that was in the original blog post. But then you can draw it out as a schematic. So here's a higher level schematic modeling that all. And if you want to sort of really understand what's going on, here's the relationship of all the different variables of how revenue from marketplaces, this is an example for Ocean, revenue from marketplaces lead to network revenue, lead to driving the fundamental valuation, combined with speculation valuation, it leads to the total valuation, which leads to the token price, and then the token price loops back to driving growth, et cetera, right? So that's an example of a model. This is all online too, by the way, just sharing. So here's some examples of results. Monthly R&D spend, given particular parameter assumptions. Marketplace's growth rate. So it's showing, in this case, by the way, it's 20-year simulations. And that's, at a fidelity of, I don't know, 1 week or 1 month. But of course, we can do 6-month simulation or 1 week simulation with higher fidelities too. So different timescales, however you like. Token count. So depending on what vesting mechanic you have, you can see what the token count is. Taking into account, vesting for your incentives program, vesting from initial investors, all of that. And then seeing, monthly Ocean or otherwise minted and burned. There's a burning mechanic in Ocean. And this actually really helped answer us a bunch of questions as we were coming up with parameters for Ocean. For example, we wanted to know, for our 51% distribution, this is vesting of the tokens to drive incentives programs. And we asked, we just said 3 different things. One is uniform, where basically, at the time, for example, Balancer had 10-year uniform investing and then just cut off, right? So we said, what does it look like? And basically, it's good for 10 years, and then it's a big drop in everything. So you just don't want something cataclysmic. So then what about exponential? How Bitcoin does it? And that looked pretty good, but we realized that for our needs, the plots aren't showing. It was too much vesting of the token in the early days when the traction really isn't quite there, right? So you can have a ratcheted exponential, which ratchets up over the first couple of years until you hit the exponential. And that can be, scheduled, the ratchets, or it can be heuristic, like Achima talked about in the previous talk. So in the case of Ocean, it's now a defined schedule. But when we designed this and initially announced, we said to be determined based on things we learned, but here are the max and min values. Okay, so that was simulation results without using the AVM side. Then, when we were going from Ocean v3 to Ocean v4, in Ocean v3 we had a problem with rug pulls. And so for Ocean v4, one of the key goals was to fix the rug pulls. And we used TokenSPICE to verify this. So what did we do? First of all, we modeled what Ocean Market was in terms of agents. So in this case, we had a publisher agent, a pool agent, which is just a balancer AMM, a staker speculator agent, and a data consumer agent. And you can have many of these, so we had many staker speculator. And then there's actions. The publisher would sell balancer pool tokens to the pool and go backward and forth there. There's pooling and staking, there's accessing and buying data sets, all of this, right? So that's the Ocean v3 netlist. And we also did one for Ocean v4 with the updated design. So this particular smart contract in the center had something called one-sided staking, and there's some other things going on. Okay, what did it look like? What's some results? So on the left, this is a simulation of the Ocean v3, and we managed to capture the behavior of the rug pulls. So here, a malicious publisher came along, and they got a bunch of people to put liquidity into the market, and then they rug pulled and got 5,000 Ocean. At the time, that was about 5,000 US dollars. With the Canada design of one-sided staking, we managed to show that it went down to just 50 Ocean, right? It's different time scales, so it's actually 50. So it's 100x lower, so basically minuscule. So this helped us to see that we had solved the rug pulls problem. It turns out that there was another issue that we didn't capture properly that ended up causing problems, but we verified this particular aspect, which was a really nice win. We were very happy with that. We also did other things. We put in vesting data tokens in the initial design, and we wanted to see that it would work. And by the way, we were verifying the smart contracts. How much time do I have? 5 minutes? Perfect. Okay. And then we also wanted to know what's the sort of overall dynamical behavior of vesting and so on. And this also had some nice results. So overall, there are some pretty cool benefits when you go to EVM, agent-based simulation. First of all, it's faster and less error-prone development, right? Because the model is the Solidity code. You don't have to port any existing Solidity code into Python, you just wrap it. You don't have to write lower fidelity equations, it's just there, right? And the cool thing about crypto, all this stuff is online, so you can go and grab these things. And even inside the TokenSPICE repo right now, we've got code from quite a few things, but it's open, you can do PRs, put into it. But there's also very flexible agent modeling. I talked about Solidity here, right? And you can do this, for AMMs with Uniswap, loans, flash loans, stablecoins, whatever. But you can also go beyond Solidity. Viper, Wasm, C, Rust, Cairo, whatever you want, right? Whatever VMs you want. You can go multi-chain, running many of these at once. You can have pure Python agents and even API calls to GPT-4 or whatever, right? So lots of things you can do there. And it really unlocks a lot, but critically for design and for verification. And it's the verification thing that I really want to emphasize, right? You've got this super high fidelity simulations, since it's using the actual code itself, but you still have to model the uncontrollable variables. These are the worst case variables, things where you don't know, you can't model it as a distribution. You have to be good across the board, right? Things like network latency. It might be very small, very large, or anything in between, or how much an LP can put in. And then there's also some statistical things too that you can model getting away with modeling statistically. And once you have those uncontrollable variables modeled, then you can do things like the worst case verification or the statistical verification or both. Okay, so to recap, right now we have TokenSPICE, the simulator. We don't have the analog verification, and I'll get to this as a call to action, but this is a recap. So I talked about how $3 billion worth of hacks in DeFi, and 75% of this was analog. And I talked about how we're basically missing this when we go to verify, right? The smart contract audits aren't covering this. We're missing the analog, we're missing the mixed signal side, and beyond one VM. But you can lump that all and just call it analog. So analog token verification. So the DeFi problem right now is the analog token verification problem because we don't actually have good analog token verification, but we can, as you've seen. So to give you a flavor here, to start with, you can just have, write a TokenSPICE netlist. Say for bridges, chain 1, chain 2, and the bridge in between, each with their own VM, et cetera, different agents. You simulate in TokenSPICE, and you could manually test different scenarios. That's a starting point, right? But then also you can bring in, TokenSPICE in the loop with AI. So here, basically, you start with the design, and then you run the verification tool automatically. And there was a comment in the previous talk about how the GUI is worse the more accurate you get. Well, this is a key thing. You actually can make awesome GUIs for this. So you have to have really good algorithms, but you can have really great GUIs. So this is the things that the analog designers who were verifying their designs, that they stared at all day long, iterating with this, plus the schematic editors, et cetera. They weren't having to write code or anything. And this is my dream here, too. So we can have these tools that have really great AI under the hood, a text-driven interface, but then there's a GUI on top that's really, really easy to use, very intuitive, et cetera. Really nice plotting, showing confidence intervals, all this stuff, right? So that can really make a big difference to adoptability. And once again, now I've talked before about the analog CAD tools. It's the same thing here for TokenSPICE in the loop. Verification, everything from nominal to fancier stuff, and design as well. And by the way, I did write a textbook on this for Circuitland that you can go and buy. It's $100 on Amazon. I get exactly $1 royalties, which they ship me every 10 years. So I'm not going to make money off of it, but if you want to have full recipes of all the algorithms, this book, Variation Over Design of Custom Integrated Circuits, is actually kind of the reference or a starting point. Okay, and so this is my dream. I dream of tool suites for analog token verification with aggressive use of AI. For fast PVT, fast Monte Carlo, high Sigma Monte Carlo, hierarchical Monte Carlo, statistical optimization, fast design sweep, all of this. Under the hood, AI like crazy. That's actually what we need for efficiency. This is my dream. And that $3 billion worth of DeFi hacks, let's make it $30, okay? And maybe we can get there, or at least 3K, but not 3 billion. That's pretty embarrassing. So to conclude, the summary is that the $3.1 billion DeFi hack problem is, right now, today, the analog token verification problem. That's the problem. And analog circuit verification has a lot to teach us. The starting point is SPICE-like simulation. And fortunately, we have an open source simulator, TokenSPICE, for that. Great. And there's other stuff, but this is the one that, it's out there, easy to use, and so on. And what we need next is TokenSPICE in the loop for analog token verification, for worst case, statistical, et cetera. So my calls to action to you, if you care about this at all, is try TokenSPICE. It's there, github.com/TokenSPICE. Fork it, build similar tools, and then build the analog token verification tools. We really need this as an industry. Personally, I would myself, but I'm really focused on making Ocean successful. But if any of you want to chase this, come to me, talk to me, and I'm happy to help guide you, because we really need this as an industry. With that, thank you very much for your time, and that's it. Thanks.
Thanks, Trent. This was super inspiring, and I mean, I really love this afternoon because you can feel this engineering spirit. So many different approaches on make things better in token land, and also become ever more sophisticated in our tools. Thanks so much. All right. We'll